Okay, guys, so today's lecture is a least square method and matrix pseudo-inverse. So we'll look at what overdetermined systems of equations are, and these are equations with like less number of variables than there are scalar equations. Uh, we'll look at what the least square solution is, matrix pseudo-inverse, and as an example, I'll give you this application, polynomial interpolation. Okay, so this is what an overdetermined system is. So we have a set of m linear equations, one equation in every row, and these involve n variables, x1, x2 until xn. And m, the number of equations, is more than the number of variables. Okay, maybe we have 5 equations and only 3 variables, x, y, z, for instance. How can we satisfy 5 equations if we have only 3 variables, right? So we have when m is greater than n, we have more equations to satisfy than the total number of variables. So clearly, unless there's some linear dependency, we cannot hope to satisfy all these linear equations separately, right? So now in vector matrix form, this is how we express this same set of equations. This is a matrix A11 through A1n. This is the first row, and the last row is AM1 through AMN. And this is the vector variable x1 through xn. And on the right-hand side, we have b1 until bm. Okay, the same system of equations I've expressed in this form. And now we have more equations to satisfy than the number of variables. So m is more than n. Here, in this matrix here, the number of rows is m, right? So the number of rows is more than the number of columns. And such a matrix we will refer to as a tall matrix. And so we have less number of scalar variables, x1 through xn, but we have more number of equations to satisfy. So on this side, we have b1 through bn. This dimension of this b vector is equal to the number of rows in this matrix. And so we can succinctly write this as ax equals b. But of course, we cannot solve it, right? Because A is a tall matrix. It has more rows than columns. Okay. Now, the ith row would read AI1 x1 plus AI2 x2 plus A dot 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 AIN xn equals BI. Okay, so this is the first row and this is the last row, the mth row. Or summation Aij, j equals 1 through n times xj equals bi. Like I said, we don't have any exact solution. So we should try an approximate solution. So we should aim to find these x's such that j equals 1 through n summation Aij xj is approximately equal to bi. And this is the ith row. And we should be able to achieve this for all the rows. This is what we aim for. When ax is approximately equal to b is what we want. Let's define the residual as the difference between these two. This is Ri. It's the difference. We want this difference to be as close to 0 as possible, right? So Ri is called the residual, which is bi minus summation Aij xj. And vectorially, R equals b minus ax, where this is the vector of residuals. Now, this Ri, the residual Ri, might be plus or minus, right? It can be on either side of the zero. We want it to be as close to zero as possible. So what we do is we take the square of it. Ri square equals square of bi minus summation aij xj. In terms of vectors, our summation I equals 1 through n Ri squared equals R transpose R. R transpose R is nothing but the square of the L2 norm, right? And so you can easily see that R transpose R equals summation Ri squared. Now, here's the overdetermined system again. So far, we haven't formally defined what we mean by this approximate sign here. Ax is approximately equal to b. Okay, now here's the residual. R equals b minus ax. The sum square errors phi x is R transpose R, which is equal to summation Ri squared. Now, this residual is also the error, right? And therefore, I'm calling this the sum square error, R transpose R. And what we want to minimize is the sum square error, SSE here, P of x. And that's why we call this method the least sum squared error. Okay? So we want to find an x to minimize the this function phi of x, which is R transpose R. And since R equals b minus ax, wait a sec. So our goal is to minimize this. And so I state this in the form of this lemma here. X, the solution to this, the minimum of this, P of x, is this. X equals A plus B, where A plus is A transpose A whole inverse A transpose. A plus is called the pseudo inverse of this matrix A. Now we go to the proof. Phi of x is R transpose R. Now R, we know, is equal to B minus AX. So this is what we have, B minus AX transpose B minus AX. And now I'll open up the parenthesis. I'll take this transposition inside first. So B transpose and AX transpose gives me X transpose A transpose, and then I open up the parenthesis. So the first term is B transpose B. Then the second term is negative X transpose A transpose B. The third term is B transpose times negative AX, which is negative B transpose AX. And the last term is two negatives will cancel out. So X transpose A transpose AX here. So this is what I'm going to prove. And this is phi of x, R transpose R. And we just showed that this was equal to this expression here, B transpose B minus second term, third term, and fourth term. Now, each of these terms is a scalar, correct? B transpose B is a scalar, and X transpose A transpose B, and B transpose AX, and they're all scalars. Now, for a scalar, its transpose is equal to itself, correct? So we can replace this third term with its transpose. Because it's a scalar, it doesn't affect this. So what's the transpose of this third term? B transpose AX. B transpose AX. Actually, what I did was X transpose A transpose B is equal to its own transpose, X transpose A transpose B whole transpose, because this is a scalar, which is equal to B transpose AX. So the second term and the third term are actually the same. Whence I will replace this with twice of this. So phi of x is B transpose B minus I, this is equal to this. So 2 times the third term here. So minus 2 B transpose AX. Then the last term is the quadratic X transpose AX. Now, so this is what I have. Let me rearrange the equations a little bit. So phi of x is, I bring the quadratic term first. So X transpose AX minus 2 B transpose AX, and then plus B transpose B. This is what I have. Now, before we continue further, let's remember something. Suppose we have a quadratic with symmetric cube. So this is a quadratic function, f of x equals half x transpose q of x plus p transpose x plus c. Okay. We want to find its minimum. What we do, we take the derivative, right?
Yes.
And what's the derivative of the first term, half x transpose qx? Since q is symmetric, del f of x is qx, right? We've seen this before. And what's the derivative of p transpose x? Simply p. What's the derivative of a constant? 0. And furthermore, the second derivative, that is differentiating this again, we get the Hessian, which is del of this, or the Hessian of this function, which is this, q. Okay. At the minimum, what we must have is this. This must be equal to 0, right? At the minimum, that first derivative should be 0. Del f of x equals 0. The same thing as scalars. And what can you say about the second derivative? If it's a minimum, the second derivative must be greater than 0. Or del square f must be positive definite. Okay? So this is how we minimize a quadratic function. This is the first derivative. We have to show that the first derivative is equal to 0, and then the second derivative is positive definite. These are the two things we have to show. Now let's proceed with the proof. This is where we were, p of x equals this expression here. Now, this A transpose A here is symmetric. Okay. And we'll call this is equivalent to our Q in that previous slide. And so let's take the derivative of this. What's the derivative of this? Think of this as Q in the previous slide. So this would be Q of x, right? Which is, there's no 2 here. This 2 is a typo. So this is simply A transpose AX. And this is negative. Something. No, this should be twice A transpose AX. And this is minus 2 A transpose B. This is the derivative of this. This is a constant term, so it's equal to 0. There's a parent. This half shouldn't be there. Phi of x is, yeah, this half shouldn't be there. That's a typo here. That's why we get a 2 here. Just make a note of that.
Hmm.
Okay, so this is the derivative of our phi of x, twice A transpose AX minus twice A transpose B. At the minimum, and of course, del square phi of x is A transpose A, 2 times A transpose A. At the minimum, the first derivative must be equal to 0. Whence, cancel out the 2's, A transpose AX equals A transpose B. Or solving, X equals A transpose A inverse A transpose B. This is the expression for the pseudo inverse of A. A plus is called the pseudo inverse of A. Now, going back to the previous step, what we have here is our goal is to try to solve AX equals B, right?
Yeah.
But what we land up instead is this expression, A transpose AX equals A transpose B. Basically, it's the same as our original equation here that we wanted to solve. AX equals B is what we want to solve. But what we are seeing here is all that we have to do is pre-multiply both sides with A transpose and then solve it. Because now, once we have A transpose A here and A transpose B here, the number of variables, that is the dimensionality of X, will equal the number of rows in A transpose A. And so this is a straightforward linear equation that can be solved. X equals A transpose A inverse A transpose B. Okay, which is equal to A plus B. A plus is the pseudo inverse of A. Now we have to show that the second derivative, it could be a minimum or a maximum, right? Now the second derivative is A transpose A. Second derivative of this,
Can I ask a question?
P of X. Compare it with this previous slide here. Second derivative of this is Q. And my claim is that this is always a positive definite matrix. Why is A transpose A always a positive definite matrix? Because by definition, this would be a positive definite matrix if for any non-zero Z, P would be positive definite matrix if for any non-zero vector Z, Z transpose PZ would always be greater than 0, right? This would make this matrix P, any arbitrary matrix P, positive definite. Now, let's replace P with A transpose A so that we must show that this is true. Z transpose A transpose A Z. Okay, we have to show that this is greater than 0. Simplifying, this becomes Z transpose A transpose, I take within parentheses, and this, I take the transposition outside, so this becomes AZ whole transpose, and then AZ, which is the L2 norm of this vector AZ. Correct? And that's always greater than 0, since Z is not equal to 0. Which is why this Z transpose A transpose AZ is always greater than 0, making A transpose A positive definite. And since A transpose A, or rather twice A transpose A, is the second derivative of our function phi of x, so at this point, x equals A plus B, x is a minimum, not a maximum. Okay, so Overdetermined systems, we want to solve this, but A is a tall matrix. It has more rows than columns. So what we do is we pre-multiply both sides with A transpose. Now, what we have here is the same number of linear equations, scalar linear equations, as the number of scalar variables, right? Because we pre-multiply both sides with A transpose. And this can be solved readily. A transpose A, as you can see, is a square matrix. Now, how do we solve it algorithmically? One method is by using Cholesky decomposition. We know that A transpose A is a symmetric matrix. And so, using Cholesky decomposition, we decompose it into LL transpose. Whence we have LL transpose X equals A transpose B is what we have to solve, right? And it can be solved pretty easily using back substitution algorithm. Remember, I told you that inverting a lower triangular or upper triangular matrix requires a algorithm of not much computational complexity in comparison to inverting any other matrix, square matrix. So X equals L inverse transpose L inverse A transpose B. Finding the inverse of L is not that hard. Now, if we have a pseudo-inverse subroutine, MATLAB has that, then we can just use that, right? We can simply let X equals A plus B. MATLAB command is PINV for pseudo-inverse. Or we can do another method called the QR decomposition, and that we shall look at in the next lecture. QR decomposition. Now here's an example. AX is approximately equal to B. We want to solve this. Here's a little example. We have two variables, x1 and x2, and we have three equations to solve. What we do is this is my matrix A, right? Pre-multiplying both sides with A transpose, this is what I have. And then I multiply this matrix and this together. This is A transpose, then A, I get this 12, 8, 8, 10, and this. And this can be solved readily, right? This side, I also multiply this matrix with this. I get this vector here, and equal number of equations and variables, and we can solve this. This is the solution that we get. Okay, here's an example of where this overdetermined systems we could encounter. We have a moving truck with some uniform acceleration. Okay, now at time instant t, it's the displacement of the truck equals the initial displacement plus initial velocity plus half times acceleration square times square, initial velocity times t at time t plus half acceleration times t squared, right? We know this. Or y equals y0 plus v naught t, which is v naught being the initial velocity, t plus half acceleration a t squared. This is high school physics. Now, we can write this as y equals a alpha naught plus alpha 1t plus alpha 2t squared. Our unknowns are, we want to find the values of this. We know t, suppose, but we don't know what the initial displacement was, initial velocity was, and what's the acceleration. These are unknowns. So we have to solve for alpha. Now we take 100 observations at different times. At time t1, we have y1 as our displacement. At time t2, the displacement of the truck was y2. In the ith time step, it was yi, and we have, let's say, 100 samples of the displacement. And from these 100 samples, we have to figure out what these alpha naught, alpha 1, and alpha 2 are. So this expression, when for each of these sample observations, T1 Y1, T2 Y2, Ti Yi until T100 Y100, we can write in this manner. Y1 equals alpha naught plus alpha 1 T1 plus alpha 2 T1 squared. Y2 equals alpha naught, since this is Y2, equals alpha naught plus alpha 1 T2 plus alpha 2 T2 squared, and so on until the last row. We have Y100 equals alpha naught plus alpha 1 T100 plus alpha 2 T100 squared. Okay. So these are the M samples we have in general. Now I'm replacing M with 100 with M. And what we have is a n minus 1 order polynomial. This is the general situation. In the truck example, we had n was equal to how much? 3, right? We had quadratic, right? We had it was a quadratic, so we had t to the n minus 1 in general. And we have a large number of samples, and this polynomial is of low order. N is less than n. So we must find these alphas to best fit our observations, these M samples. And the unknown coefficients are alpha naught, alpha 1 until alpha n minus 1. This is an overdetermined system. Okay. I'll write down this expression for each of these observations separately. So y1 equals this equation with t replaced with t1, t1 squared until t1 to the n minus 1. Likewise, y2 equals alpha naught plus alpha 1 t2 plus alpha 2 t2 squared, and so on until the last observation, the mth sample. So this is what I have to solve for, right? The alphas, alpha naught, alpha 1 until alpha n minus 1 are the unknowns. Rearranging them in vector matrix form, this is what I have. These scalar set of equations give me this single equation, linear equation in vector matrix form. And what are the number of rows? M. The number of columns is n, which is actually, it doesn't look so here, but the number of rows is more than the number of columns. This is of the form V. This matrix here is V alpha equals y. And we have approximately equals y. And so the solution is alpha equals V plus y. V is called the van der Waals matrix, by the way. It's this tall matrix here. Any questions?
No.
No.
I have a question on A
I can't hear
transpose
you.
A. Hear me now? Hello?
Yeah, okay, go ahead. I'll try to.
Yeah, so I wanted to ask what conditions must there be on A transpose A for it to be invertible?
It must be, that's a good question. A transpose, so this must be a full full column rank matrix. If it's a 3 by 2 matrix, then its rank must be 2. So here, uh, here we have m rows and n columns, right? So the rank of this matrix must be n.
Okay.
If it is not equal to n, then we can actually do a linear transformation and reduce the number of variables.
Hmm.
So it effectively means that the variables should be linearly independent of each other. Then
What's that?
the variables should be linearly independent of each other.
Variables cannot be linearly, there's no such thing as variables being linearly independent or dependent. But the columns
The
of this
columns,
matrix A must be linearly independent.
so that it will be a non-singular matrix.
No, again, there's no such thing as singular and non-singular in this case because it's not a square matrix.
Okay.
It's a full column rank matrix.
Full rank. Okay.
Okay, in fact, what we are doing is converting this into a non-singular square matrix, A transpose A, right? So what we're trying to solve is this A transpose A x equals A transpose B. Now it becomes a square matrix, and we saw that it's a non-singular matrix because it's
Non-singular.
positive definite.
Yep.
Okay. Now, if A were not a full column rank matrix, then A transpose A would not be invertible.
Hmm.
This is the solution, right? Where is
Yep.
it? Yeah. This is the solution, right? X equals A plus B, where this is what happens. This is A transpose A inverse. We are assuming that, well, we know that A transpose A inverse exists because we assume that A is full column rank.
Mm-hmm.
Any other questions?
Nope.
No.
Okay, so now what I'll do is let's stop this and we pause the. Okay. So we'll look at a couple of examples. Actually, we'll look at 4 examples, not just a couple, to help you do homework that I have given. So before we begin with the first example, note that if B is some singular matrix, singular square matrix, then its columns are not independent, right?
Yep.
Hence, there must be some vector z which is not equal to 0 such that bz equals 0. So this is an observation we use for B to be a singular matrix. Now here's one example. This is the matrix B, and it is singular, known. In fact, the rank of this matrix is just 2. Now, this z, so there is some z here, right? What the statement says is that there is some z which is non-zero, such that the matrix times z equals all zeros. And in fact, for this matrix here, because it's singular, this matrix times this vector here is all zeros. Okay. Conversely, if B were non-singular, then the only way we could make BZ equals 0 is when Z equals 0. So how do we show that a square matrix B is non-singular? we show that for any arbitrary vector z, if bz equals 0, then it must be the case that z equals 0. Okay, that's how we will prove. And that will help us address question 1 in the next slide. We'll use this. Okay. Now, this is the first example. We are given a n by n positive definite matrix Q. And we have A has full row rank n. A is an m by n matrix, and this is an n by n matrix. And so B is given by this matrix here. We have to show that this block matrix here is non-singular. If this is positive definite and this has full, A has full row rank n. Okay. How do we prove it? We'll take a block vector xy and assume that b times this block vector equals 0. By the way, the subscript is for you guys to follow. This 0 here is a m by m matrix of zeros, and this is a n plus 1, sorry, n plus m times 1 vector of all zeros. Always when you deal with block matrices like this, pay attention to the dimensions. Okay, so what we have to prove is, since this is B, we're assuming that this is equal to 0. What do we have to now show? Bx equals 0 can only happen if xy is 0, right?
Xy 0, yeah.
That's what we have to show. We have to show that this vector, block vector xy must be equal to 0. Only then would b times xy be equal to 0. Okay, that would show that b is non-singular. Okay, so here's b. I'll plug in the values of b, and this is xy here. And let's proceed with the matrix multiplication. Qx plus A transpose y and Ax plus 0y, so Ax. And this is 0. This is 0 sub n, n-dimensional vector of zeros. This is m-dimensional vector of zeros. Okay. Whence Qx plus A transpose y should be equal to 0. And separately, Ax should be equal to 0, right? For this to be all zeros, we must have Qx plus A transpose y equals 0, equation 1, and Ax equals 0, equation 2. From 1, Qx plus A transpose y equals 0. Pre-multiplying both sides with X transpose, we get X transpose Qx plus X transpose A transpose y equals 0. Now I club this together, X transpose Qx plus Ax whole transpose y equals 0. From this, since Ax equals 0, Ax transpose must also be equal to 0, right? And therefore, since Ax equals 0, Ax transpose must be equal to 0. Therefore, Ax transpose y must also be equal to 0 from 2. I just replace Ax with 0 here. And so this term vanishes. So what we are left with is X transpose Qx equals 0. Are you guys with me so far?
Yes.
Yes.
So X transpose Qx equals 0. But what were we given? Q is a positive definite matrix. When can X transpose Qx be equal to 0? Only when X is a vector of zeros. correct? So we arrive at this. X must be equal to 0, this X here. But we have to show that Y must also be equal to 0, correct? So if X equals 0, now look at this expression. From this expression here, if X equals 0, then A transpose Y must also be equal to 0, correct?
Yes.
But A has full row rank, whence A transpose has full column rank. So it can only be 0 if Y equals 0. And so we show that X and Y both are equal to 0. Therefore, for this B times this block vector to be equal to 0, this block vector itself has to be 0. Therefore, B is non-singular. Are you guys with me, or any questions?
Yeah, with you.
Yeah, clear.
Doctor, a little question.
Sure.
Was it possible to assume in the beginning that, for example, from equation 2, yeah, that equation with ax equals to 0, was it possible to assume that x is equal to 0 because a is full row rank without doing that first steps? Am I clear?
Um, Sorry, I couldn't, it's not quite audible, but just hang on. Maybe my volume, let me try to turn on my volume. Yeah, go ahead once again, Daniel.
Okay, in the equation 2,
Yeah,
we have ax equals to 0.
right.
So was it possible to assume from this equation that x is equal to 0 without doing that process, because a is a full row rank, because that is why I could do it. Yeah, so
But
is it possible
or
to do?
is it possible that ax equals 0, although x is not equal to 0, because a is full row rank? Uh,
Yeah, or x.
Even then, even if that were the case, right?
Yeah.
X transpose QX is also equal to 0. So it doesn't affect this conclusion here, that X transpose QX equals 0. Okay, I see, which implies that X must be equal to 0. So what you're saying is X is not equal to 0, but AX is equal to 0,
No.
right?
No,
But
no, no. My question is if we could get the same result only from equation 2. Yes, only because A is full row rank. Because that is what I could do. I could do without the process. So, and my question is if it is correct to do.
but we have to show that X equals 0,
Yeah,
right?
yeah.
Yes, sir. Let us say we start from this equation 2, which says that ax is equals to 0. Now,
Mhm.
A is already a full row rank matrix.
Mhm.
So, since A is already a full row rank matrix, ax will be 0 only if x is 0.
Oh,
Yeah. So could we do directly from, could we?
I see what you mean.
Yeah.
Oh, let me see. A is full row rank.
Yeah, that is my question.
Yeah, but look at this. A is full row rank, right? So which
Yeah.
is more, M or N?
Mm, M is more.
M is more. So this is a tall matrix, correct?
Yeah, yeah.
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 So if it's a tall matrix and it's full, so the rank of this is n. All its columns are linearly independent,
Yes.
right?
Mm-hmm.
Yeah.
So what you're saying is, which means that x must be equal to 0.
Yeah.
Yes.
X must be equal to 0. Actually, that's a good question.
Because that is the very fact which we are using to prove that y is equals to 0.
Yeah, in line
Yeah,
the
yeah,
very
yeah,
last line.
yeah. I get. Yeah, you could do that. And then how do you prove that? Yeah, actually, that's correct. So mine is an indirect way to do it. I just had to use this property here, that assumption that Q is positive definite. Now, yeah, what if we did not make this assumption?
Sir, in that case, it would be difficult. How would we prove that y is 0? Because,
We cannot prove y is 0. Yeah.
yeah, because in proving y is 0, we have to use the fact that A is a full row rank matrix.
Yeah, yeah, yeah. That's
Does it differ if we have full column rank?
no, it can't. I have to look at the full column rank. Maybe that's the case. Yeah, that's it's possible. If you have full column rank, then A is a tall matrix, correct?
Yeah. And that's the least squares matrix, the skinny matrix.
Yeah, that's probably what it is. It's got full column
Yeah.
rank. Yeah, sorry about that. Okay, now let's move on to the next example. So that was it. Thank you, guys. I think Dania was the one who first pointed it out. So, but thank you all of you. So
Okay. Thank you very
this
much.
should have been full column rank. So our next example. Okay, now remember that del P transpose X is the same as del X transpose P, which is equal to P. And we must show that derivative of A transpose X, X transpose B is equal to AB transpose plus BA transpose times X. Now, what I do is I take the first two factors here, A transpose X, as one factor, and then likewise I club X transpose B together. So that's my second factor. And then I proceed to do the derivative. Okay, I have to show that this left-hand side, this derivative of this whole thing, is equal to the right-hand side. Now, from calculus, we know that the derivative of the product of two functions, fg, equals the first function f times the derivative of the second function plus g plus the derivative of the first function f times the second function g, right? And so we apply this familiar equation here. So this is the first function, A transpose X. What's the derivative of X transpose B? It's B. And then what's the derivative of A transpose X here? A. A. A times X transpose B. Now, since X transpose B is a scalar, I can replace it with B transpose X, right? And so I have B A transpose X plus A B transpose X, which is equal to B A transpose X plus A B transpose X. Then I take X common on the right. So I have BA transpose plus AB transpose X, which is what I had to show. This is a simple question, right?
Yeah.
Okay. Example 3. We have a matrix A, square matrix, and we have an approximate eigenvector X. X is not an eigenvector, but it's very, very close to an eigenvector. Now we want to estimate what's the corresponding eigenvalue. How do we do that? So we assume that AX is approximately equal to lambda X. Okay, since X is an eigenvector of A, and we assume that lambda is the best estimate of the eigenvalue. When X lambda, instead of lambda X, I'm writing X lambda minus AX is approximately equal to 0. We have to minimize, we have to find lambda, right? So lambda is our variable. We have to minimize this function, the square L2 norm of X lambda minus AX, which is this. So Vx is equal to X lambda minus AX transpose X lambda minus AX. And when I open up the brackets, I get X transpose X lambda squared and negative 2 X transpose AX lambda plus X transpose A transpose AX. Taking the derivative, I have del phi of X equals derivative with respect to lambda. I want to minimize with respect to lambda. So this is actually a little misleading. It should be, it's a scalar derivative, right? Instead of a gradient, you can just replace it with d over d lambda. So anyway, the derivative of phi of lambda with respect to lambda is this. What's the derivative of this? Twice X transpose X lambda. Derivative of this term is twice X transpose AX, and this doesn't involve lambda, so derivative of this is 0. So this is what we have, and at the minimum, this del phi of lambda must be equal to 0, whence X transpose X lambda is equal to X transpose AX. Hence, the best approximation is lambda equals X transpose AX over X transpose X. If X is a unit vector, even better. Lambda is simply X transpose AX, because denominator is positive. Okay?
Yes.
Okay, example 4. So we have an SPD matrix A, symmetric positive definite matrix A given to us. And so it's positive definite and A transpose equals A. And we have to show that the diagonal elements of A are positive, strictly positive. AII is greater than 0. Okay. So how do we show this? All the diagonal elements. This is a proof by induction. So what I do is I express this matrix A in terms of the very first scalar element A11. I isolate this. This is A for I equals 1. This would be A11, right? I'll show that A11 equals is greater than 0. Then I'll show that A22 is greater than 0. And then I'll show that A33 is greater than 0, and so on. So let's isolate A11. Okay. So let the rest of the column excluding A11 be denoted as A21. This is a column vector. Okay, and since A is symmetric, excluding A11, the first row should be A21 transpose. Correct?
Yes.
And the excluding the first row and the first column, this block is A22, this matrix. Now let's take any arbitrary vector x equals x1 scalar, just like we isolated the very first scalar term A11 here. Here x1, and then x2 is a block vector of one less dimension than x. Just like this A22 is a well, it's symmetric too. It's a one less dimension than A, right? Okay, and so we have to show that the diagonal elements of A are positive. Now, since A is positive definite, X transpose AX must always be greater than 0 as long as X is non-zero, right?
Yeah.
Or now, plugging in the values, we have X1, X2, X2 transpose. X1 transpose is X1, right? Because it's a scalar, times this whole block vector here, block matrix, times this block vector x1, x2 is greater than 0. Now let's proceed to do the multiplication. When I multiply this block matrix with this block vector, I get this, and then I multiply it with this row vector, and it simplifies to this. Any questions so far?
Mm,
No.
Okay. And now we can see that the second term and the third term are actually the same, because they're scalars and one is the transpose of the other. Whence this x transpose AX reduces to A11 x1 squared plus twice x1 A21 transpose x2 plus x2 transpose A22 x2 greater than 0. Now, x is anything arbitrary, right? We are free to choose any x. And anyway, this is greater than 0. This is what we landed up with. Now, what I'll do is I'll take this x1 common, and so this is what I have. A11 x1 plus twice A21 transpose x2 times x1 plus this quadratic term here, x2 transpose A22 x2 equals, sorry, greater than, is greater than 0, strictly greater than 0. So now let me go to the next slide. This is what I landed up with. This. Now, since I'm free to choose any value for this, as long as it's non-zero, why don't I choose x1 to be some non-zero value and x to be a full vector of zeros, and see what I get? What will happen? This term here will disappear and this term here will disappear. Hence, A11 x1 square is strictly greater than 0. Right? Now, x1 is not equal to 0. x1 square must be greater than 0. What can you infer from this about A11?
greater than 0.
It must be greater than 0, strictly greater than 0. So we showed this for I equals 1. A11 is strictly greater than 0. Now let's assume that x1 equals 0 and x2 is some non-zero vector. Okay. This is what we showed. So now let's do the other case. x1 equals 0 and x2 is a non-zero vector. Whence, from this expression here, what do we get? Since x1 equals 0, this term disappears, this whole thing disappears.
Yeah.
Right? It has x1 in it. So this whole thing disappears, first term, which means that x2 transpose A2 to x2 is greater than 0. x2 is any non-zero vector. What can you infer from here?
A22 is greater than 0.
It's positive definite. So A22 is positive definite, right? So this is positive definite. What we proved is that the first scalar element in the first row and first column is positive, and the rest of the matrix is positive definite. Now, since this is positive definite, now pretend that A22 is equal to this A. So we can then isolate the first row and first column of this matrix, right? And this matrix would begin with A22, right? Instead of A11, it begin with A22, right? And
But
so
we use the same proof to prove that
the
is
same proof, basically, exactly.
okay.
So A22 is greater than 0.
Okay.
And likewise, we can proceed A33, A44, and so on. Everything is greater than 0. Okay.
Yes.
Okay. So, are there any questions?
No.
I have a set of 18 problems in my lecture notes, and that can help you in solving the homework. Okay, so see you guys.
Thank you.
Thank you very much.
Bye.
Bye.
Bye.